Hello and warm welcome to everyone. So today we'll be starting the week 7 of the course on financial econometrics. So in the last few lectures, we have talked about the univariate time series modeling. So here what we assume, the current observation of any series depends on its own lag or on the lag of the random error terms or on both. However, we will see that there is a certain macroeconomic financial relationship where the current observation of any series does not depend only on its own lag, rather than it also depends on the other variables. So in such cases, we need the multivariate time series modeling approach. In the previous lectures, we have discussed a structure of this where the yt, the current observation of the series y, depends on its own previous lag. What specifically we have called it the autoregressive structure, or we have discussed where the current observation yt depends on the previous term of ut, or the combination of both. So there are the certain relationship where what we have seen that the current observation of any series not only depends on its own lag, rather instead it also depends on some other variables. So in such cases, this is the very restrictive approach is there, and univariate time series modeling may not be appropriate of such relationship. For example, let us think of the relationship between GDP, investment and consumption. Yes, the GDP do depends on its own previous observation. However, the investment or the consumption also have effect on the current observation of the GDP. Similarly, if we think of the bond yield, it depends its own previous lag, but it also gets affected by the interest rate. So in that cases, such kind of structure is not appropriate, and it leads us to the multivariate time series modeling approach. In case of multivariate time series modeling approach, what we do here, this yt, the current observation y, not only depends on its previous lag, but it also depends on the current or the past observation of the another series. In this structure, what we call the exogenous variables. So this gives the idea of the contemporaneous term and the lagged values. So what we call the current value of yt depends on the contemporaneous and the lagged values of exogenous variables. Here we have represented it using the zt, where the beta 0 and beta 1 are the coefficient of the contemporaneous and the lagged values of zt here. Does it solve the problem? Yes, there is the partial solution where the yt depends on not only on its own lag but also on the lag of the another variable. Let's call it here the exogenous variable zt and the lagged values of zt minus lagged values of zt. However, this is not a complete solution. Why? There is a certain macroeconomic or financial relationship where not only the zt is the exogenous, but zt also might depend on the yt. So that is, the exogenous variable also may depend on the endogenous variable yt. For example, let us think the theory of multiplier theory and the accelerator theory in economics, where the multiplier theory says that income depends on the investment. So if there is the change in the investment, the income will change. On the other, the accelerator theory says that if there is change in the income, the investment will change. So here both income depends on the investment and the investment depends on the income. In such cases, this particular model does not solve the problem. And this leads us to the idea of simultaneous equation model. So one of the solution of such relationship is the simultaneous equation model. However, we have discussed in the earlier that there are the certain issues we have with the simultaneous equation model, especially the simultaneity bias creates the problem. Then Christopher Sims in 1980 introduced a very seminal model, what we call the vector autoregression model, which basically takes account the problem of the simultaneous equation model. And again, the vector autoregression is nothing but the example of the multivariate time series approach. Today basically we will be talking about what is the vector autoregression, then the various aspects of the vector autoregression. That is one of the dominant example of the multivariate time series modeling. That is the vector autoregression. So let us formulate a bivariate system where yt depends on its own lag and also on the contemporaneous and the lagged values of zt, that is another series. And zt also depends on the current contemporaneous value of yt, that is the current observation of yt, and also on the previous observation of its own and of yt. So here, what are the endogenous variables we have? Since both yt and zt is determined within this system, so the both yt and zt are the endogenous variable. What are the assumptions we are assuming here? So we are assuming that first, both yt and zt are stationary in nature. Second, the disturbances epsilon yt for the equation of yt and epsilon zt for the equation of zt are white noise process. That means the deviations, standard deviation are constant, that is the sigma y and sigma z, and basically they captures the random shock of the system. The structure which has seen here, that is basically nothing but one of the example of the VAR structure. So what is the VAR model? So VAR model is basically that model where each variable is a function of its own lags and the lags of other variables or the contemporaneous terms of other variables. So here allowing a detailed view of interdependencies, that is yt depends on zt and zt depends on yt. Basically this Stock-Watson has defined VAR in very succinctly that VAR is an equation and n variable linear model in which each variable is in turn explained by its own lagged values plus current and past values of other variables, that is the remaining n minus 1 variables. So that's the basically definition of VAR which we have represented here. So another important thing here we have to mention, there is the feedback mechanism. Feedback mechanism basically the structural VAR models or in the privative models allows yt and z to influence each other, that is both immediately, that is there is a contemporaneous relations between yt and zt. So for example, yt is affected by both its past values and the lagged values of zt, and similarly vice versa, the zt is being affected by its past values plus the current and past values of yt. What are the impact of parameters we have? How we assess that? So basically what we can see, the immediate impact of zt on yt is presented by minus beta 1 0, and the lag impact is represented by the beta 1 1 and reflects that how zt minus affects yt. Similarly, we can say that the immediate impact of yt on zt is captured by alpha 2 0 and the lag impact is represented by alpha 1 1. So that is how yt minus 1 affects zt is represented by alpha 1 1, and how the current value of yt affects zt, that is the immediate impact, is captured by the alpha 2 0. Let us generalize this vector autoregression for the k period. So we are not restricting to lag 1, so let us generalize. So if we generalize that, then what we can observe here, the current observation yt depends on the current observation of zt and also the lag terms of zt and up to lag k, and the lag value of yt from 1 to k, it also affects the yt. Similarly, we can represent the zt, so that zt is affected by the current and the past observations of yt and its own past observation up to lag k. So this form is nothing but the vector autoregression of order k. This can be also generalized for the m variable. So that is, this analysis could be extended to the VAR m model, where there are the m variables and m equations we will have. So here we have the example of the two equations. However, there the issue of simultaneity we have, which brings the estimation challenge in this particular structure. So what is the simultaneity issue we have? So what we can see, when yt and zt appear in each other's equation contemporaneously, they influence within each other within the same period. So if that is the case, then what we can observe from the equation here, this creates the simultaneity issue. How? In case of ordinary least square, what we have assumed that the error terms are not related with the explanatory variables. However, if we look here in this our case, what we have this yt is equal to beta 10 plus beta 10 zt plus, so here what we have, yt is equal to b10, that is the constant, plus beta 10 zt plus alpha 11 yt minus 1 plus beta 11 zt minus 1 plus epsilon yt. And zt is equal to, we have beta 20 plus alpha 20 yt plus alpha 21 yt minus 1 plus beta 21 zt minus 1 plus epsilon zt. So here what we have, yt is equal to beta b10 plus beta 10 zt alpha 11 yt minus 1 plus beta 11 zt minus 1 plus epsilon yt. Similarly for the zt we have b20, that is the constant, alpha 20 yt plus alpha 21. So what we can observe here, this yt depends on the current value of zt, and here again the zt depends on the current value of yt. So this the zt now since this zt depends on the yt, therefore there will be the correlation between zt and epsilon yt. Similarly, since this yt depends on zt, therefore there will be correlation between yt and epsilon zt. So this basically violates the assumption of OLS, where we assume that the explanatory variable is not related with the error term. So in such cases, this OLS estimates will be inconsistent and biased. So until unless we to account for these contemporaneous interdependencies, we will not be able to estimate the this VAR system. So what is the solution of that? The solution is the reduced form equation. So before discussing what is the reduced form equation, let us represent this structural form into the matrix notation. So for this, for the simplicity here, we are assuming the lag bit is 1. So the value of k is 1. So in that case, what we can write, yt is equal to b10 plus alpha 11 yt minus 1 plus beta 11 zt minus 1 plus beta 10 zt. So this is the contemporaneous effect of zt on the yt, and this is the lagged effect of zt. Similarly, we can write zt like this, and this can be represented in the matrix format as here. So here the yt and zt is the basically k by 1 vector of the variables. Here so here the yt and zt represents a column vector representing the number of variables, and here the number of constant, again this is the column vector, and here we have 2 by 2 matrix representing the parameters, and this is the again column vector of the variables, and this is again the parameter coefficient matrix, and zt yt is again the variable here, and these are the basically error terms. Or we can represent this form of the vector autoregression is basically known as the where in the primitive model or primitive form, or we also sometimes call in the structural form. Now let us take the continuous term in the left side. So we are taking the continuous term the left side, then what we have 1 minus beta 1 0 and minus alpha 2 0 into 1. So yt is equal to zt. Now this can be reduced. Ayt is equal to b0 b1 yt minus 1 plus ut. Here A is nothing but this matrix of this coefficients, and yt is nothing but the yt and zt, and b0 is basically the constant terms, and beta 1 is the here the parameters, and yt is basically nothing but the lagged values of yt and zt, and this is the error term. Now if the matrix A is there, then we can take the inverse of this matrix, that will be nothing 1 upon the determinant of matrix A multiplied by adjoint of A, which turns out to be this. Now if we multiply both sides using this A inverse, what we will get? A into A inverse is identity matrix, that is only the matrix of yt, that is the endogenous variables will be there. A inverse beta 0 b0 plus A inverse b1 yt minus 1 plus A inverse ut. Or we can represent this in yt is equal to a0 plus a1 yt minus 1 plus et, where a0 is nothing but the A inverse b0 and A inverse b1 is equal to a1, and A inverse ut is we are representing by et. So this equation basically is known as the nothing but the reduced form of equation or standard form of VAR, and we will see that the VAR in this form we will be able to estimate. Let us first see what are the properties we have here. So how we will calculate the first error term? So we can calculate the transform error term Eyt and Ezt like this. So here Eyt is nothing but epsilon yt minus beta 1 0 epsilon zt and 1 minus beta 1 0 and alpha 2 0. So this is the basically the value of Eyt depends on the epsilon yt as well as on the epsilon zt. Similarly, we can calculate the Ezt. So the structure of these error terms is different than the original error terms. What are the properties of such error terms we have? That these error terms are white noise. The error terms are white noise with zero mean and constant variance. However, an interesting feature is that these error terms will be correlated to each other, and the covariance between these error terms we can measure using this particular equation here. So this is the unique properties we have. Okay, the error terms in the reduced form will be correlated to each other. That is, one shock of the variable will affect the shock of another variable. Then what is the variance covariance matrix? From the error terms we can create the variance and covariance matrix. So what we will have, this covariance is basically non-zero, implying that the two shocks are correlated. However, if beta 1 0 is equal to alpha 2 0 or 0, so that is if the contemporaneous correlation coefficients are 0, then that means if the beta 1 0 and alpha 2 is equal to 0, that means there is no contemporaneous effect. If that is the case, then the shocks will be uncorrelated. And here we define the variance covariance matrix of Eyt and epsilon zt as here sigma 1 square, that is the error term of this, and the sigma 1 2, that is the correlation between this, and here sigma 2 square. So this is the basically variance and covariance matrix. What will be the correlation implication? If they are correlated, what will be the implication of that? So if the sigma 1 2 is not equal to 0, that means this Eyt and Ezt, that is the both shocks are correlated to each other. When this 2 is equal to sigma 1 2 is equal to 0, that is when the correlation is equal to 0, that means these are the independence, which basically simplifies the analysis. However, in such cases when they are correlated, we will see how we find out the estimates and how we use the vector auto-regression. Then before using the vector auto-regression, we have to certify some condition, that is the stability requirement. So for a vector auto-regression model to be stable, the roots of the characteristic polynomial here 1 minus alpha 1 1 L and 1 minus beta 1 1 L minus alpha 1 1 beta 1 1 L square, this must lie outside the unit circle. So what we mean by the stability or the parameter stability? See, basically parameter stability means the systemic convergence. What we mean that? This stability basically implies that the series of yt and zt remains bounded and they are predictable. So if the parameters are not stable, then it may be the case of explosive where the prediction is not possible, forecasting is not possible. Therefore, we need the stability, parameter stability of the vector auto regression. However, once we reduce the structural form into the, once we convert the structural form of the vector auto regression or the primitive form into the reduced form, there is a certain instructions, certain issue we face, and solution of that issue what we call the identification in structural way. So basically what we mean here is that our goal is to basically estimate the primitive model, but however we are not able to estimate, then we reduce, you change it to the reduced form where we will be able to estimate. But our objective is basically use this estimated value to make the inference about the primitive VAR. So this identification is basically refers to the process of recovering the parameters of the primitive VAR. So we are estimating the reduced VAR, but we wanted to find out, obtain the parameters of the primitive VAR. So how we will do that? So this identification basically refers that process. So here we have IT and ZT here. So we have the challenge to estimate this direct model. We will not be able to estimate that. So what we due to the simultaneity issues, then what we do, we are not able to use standard methods like the OLS and all to estimate this particular thing. So what we do to solve this simultaneity issue, we reduce that vector autoregression. So by reparameterizing this structural equation, we can apply the OLS. So this enables the estimation of the two intercept in matrix A and the 4 autoregressive coefficient in matrix A1. So we will be able to estimate this. Now after estimating this reduced form VAR, these residuals from this two regression, if they are able to give the estimate, so once we estimate, then the residuals of these two regressions gives us the estimate of the variance of EYT and EZT and their covariances. Now the main question we are facing is here this: can this residual fully recover the structural parameters from the reduced form estimates? So we have these estimates. Can these residuals will help us to find out the structural parameters? So we will see that without imposing any restriction on this, the answer is no. We have to put the certain restrictions to go back to the original primitive VAR, because the structural system is under-identified. What we mean by the under-identified, let us get that by comparing the parameters. So reduced form VAR provides 9 parameter estimates, that is 6 coefficients, 2 constant and 4 the autoregressive coefficients, and 3 residuals statistics, that is the variance of EY and variance of EZ and the covariance between these error terms. However, in case of structural system, what we have the 10 parameters, 2 intercepts, 4 autoregressive coefficient and these 2 feedback coefficient or the contemporaneous coefficient and 2 variances for YT and ZT. So here we have 9 parameters and here we have the 10 parameters. So using these 9 parameters, we have to get the 10 parameters. That is basically not possible. Therefore, we put the restriction, what we call the identification restriction. So the structural system requires then additional restriction to resolve this one parameter under identification. So how we do that? How we impose the restriction and how we get the identification. So recursive system with the zero restriction. Let us put the zero restriction. So one common approach to identification is impose a zero restriction on the structural system. So any of the contemporaneous effect, we assume it is equal to 0. For example, here alpha 2, we are assuming the value of alpha 2 is 0 is equal to 0. That basically what we are assuming, that zt has an immediate effect on yt, while yt affects zt only with the lag term. So there is no immediate effect of yt on the zt. Actually, this leads us exactly identified system here. So let us see here, under alpha 2 equal to 0, what we have, epsilon yt, error term of y is nothing but the epsilon yt minus beta 1 0 and epsilon zt. However, the epsilon zt is nothing but now, error of zt is equal to the epsilon zt. And due to this, what implications we have? This recursive restriction aligns the model with the economic theories, where the certain variable may affect the others with the delay. So there are the many economic theories where we can assume that, for example, assuming that investment will have immediate effect on GDP is quite irrational. So GDP, the investment of the current observation may not have impact on the current GDP, rather than it may have effect on the future GDP. That means the investment do affect GDP with the lag term. So sometimes this solution helps us to find out the primitive VAR model from the reduced VAR model. Now, how we solve this parameter basically? So what are the system efficacies we have? By using the variance and covariance matrix of these residuals, we can solve for unknowns like alpha 1 0, sigma square y and sigma square z, because what we have assumed that the other coefficient of other variables is 0. So we can find out variance of yt here, variance of t and covariance between these, like assuming this we have been assumed. Then once we have variance covariance, we use the Cholesky decomposition basically to find out the estimates. So what we do basically in the Cholesky decomposition? Cholesky decomposition basically bifurcates any square and positive definite matrix into the true triangular matrix in such a way that the multiplication of those two triangle matrix is equal to the inverse of that matrix, and it basically helps us to identify the process. However, there is a certain assumptions we have in Cholesky decomposition. What assumptions we have? That the first variable, if we order the variable like let's say yt and zt and let us say xt like this, that this first variable will have effect on zt as well on the xt. However, zt will have effect only on xt but not on yt. Similarly, xt cannot affect the zt and zt cannot affect the yt. So this is the sequence order we have, and the Cholesky decomposition help us to identify the shock of yt, zt and xt, how it has effect on other variables. But with the certain restriction, that restriction is that yt will have impact on zt and xt. However, zt and xt cannot have effect on the yt. That means the ordering of variable does matter in the Cholesky decomposition. So we can generalize this. What we can generalize, for an n variable where this Cholesky decomposition allows exact identification by placing n square minus n upon 2 restrictions, that using a triangular matrix structure to estimate the relationship among the variables with recursive restrictions. So if we are using the Cholesky decomposition, then we can get the parameters of the primitive var from the reduced var. What are the limitations we have for var models? Despite its forecasting strength, var lacks the structural insight. Why it lacks structural insight? Through the var, we will not able to explain the structural relationship, rather than we can easily forecast. Here, it cannot provide policy predictions or causal explanation due to the no restriction. So, if you are not putting restriction, then we will not be able to find out the primitive var. If you are not able to find out the primitive var, then that means we will not be able to suggest anything about the policy, or we cannot explain the causal relationship until unless we put the restriction. So, such kind of model cannot be used for the analyzing the economic interrelationship between the variables. However, we have to put the identification restrictions which are arbitrary. However, there is the solution what we call the structural vector autoregression, where we put the restriction derived from the theory. So, that is what we are going to discuss into the next class. Another advantage we will see in the structural vector autoregression is that it helps us for the explaining the unexpected shocks. So, today basically we have discussed what is the var and formulation of vector autoregression, certain conditions for the estimation we needed. In the next class, we will see how we put this restriction derived from the theory which comes under the structural vector autoregression. Then we will also discuss about the causal relationship between within the system of vector autoregression. So, for the time being, thank you. Hope you are enjoying the lecture. So, in the next class, we will be discussing the next part of the vector autoregression. See you there. Thank you so much.